welcome to the very first science demonstration of the channel. I'm very excited to show all this material for you because there's been a lot of preparation and it involves my element collection. So without further ado, let's begin. Alright, so I'm going to start with a little bit of an explanation as to what is going on here. So how it was set up. One moment here. Okay. So the experimental setup, okay, involved a Tesla coil that I acquired from a coworker, and he was willing to part with it. And the way it works is that it uses an AC adapter to connect to a series of electronics, including a bank of capacitors that will build up charge over a period of time, and it will emit a repeating amount of sparks. The mason jar has a piece of sticky tack, and with it I attach the small glass bulbs, which I'll show you here. This photograph was taken when I first obtained some of these samples. So this one in particular is helium. Okay. So as you can see, they're perfectly clear, and ordinarily you would not be able to identify it just by looking at it. All the elements contained within the glass ampules are clear. Even the sample of chlorine is clear because it's at a low pressure, so you don't see the titular greenish yellow that comes off of thick chlorine gas at 1 atmosphere. So what goes on in the experiment, okay? Alright, so when the power is turned on, the electric charge will begin to build up around the needle, and in particular the extremity. Alright. So this is normally what happens with conductors, especially like if you what's a good example? So if you were to rub just a static electric charge and displace it onto like a piece of aluminum foil, the extremities of that aluminum foil is where the charge would gather on the conductor. Okay, so the corners of the aluminum foil. So much like the formation of a lightning bolt, okay, the charge here will inevitably polarize anything that is towards the closest end. So this one will be positively charged, and the electricity will want to jump over to the other object. Now, what you'll also see in the videos is that many of the bulbs will light up before it is even struck by one of the sparks. The reason for this is because since there is a buildup of negative charge on the needle, it's exerting an electric field that permeates through space, okay? And this exerts an electric potential over a distance, and so any electric charge will want to accelerate across this potential, okay? So, and this will cause a flow of electrons through the gas bulb, okay? Excuse me. So, in the first example with hydrogen, this is most notable, is that there will be these strange pancake-looking regions in the bulb. And you'll probably have seen this before if you've ever looked at a fluorescent bulb when it's cold outside, or it's in a cold environment. So, the reason for this is because the excitation of the hydrogen within the bulb corresponds to specific energy levels. This is where we get the term quantum mechanics, because it relates to specific quanta, or quantities of energy. Okay? In the practice of exciting hydrogen and analyzing its spectrum and comparing it to like a predicted set of numbers is actually something that's very common for undergraduate physics when you first enter quantum mechanics. So you'll explore the three-dimensional model of the hydrogen atom, and you'll go over the Rydberg energies as well as the corresponding wavelengths, and all of them will deal with first, like what it means to energize the electron, and then for it to drop down to a specific energy state. So, for an electron to go from the ground state, or the base, or the lowest energy, okay, to all the way up at the top, okay, you can imagine that the energy of, or the energy potential is like a gravity well, okay. The electron will be excited up to the valence, or the valence energy, and that will that energy corresponds to around 13.2-ish electron volts. Okay. Now, it doesn't necessarily need to jump up to that energy level, but it may jump up to the 6th, the 5th, the 4th, the 3rd, the 2nd, etc. And then from that excited state, it will want to jump back down after a short period of time. And when I say a short period of time, it's on the order of nanoseconds. Okay? So, the energies that we're talking about here. Alright, so let me pull up the Rydberg states. Let's see here. Okay. Oops. I'm gonna move me across the window. There we go. Alright, so the ground state is energy level 1, okay? And the electrons can jump up to any number of states above that, as explained before. So the energy required to get it completely outside of the hydrogen atom would require about 13.2 or 0.3-ish volts, I want to say. But the light that you see from the hydrogen atom is from the demonstration is them being excited to the 6th, 5th, 4th, or 3rd energy states, and then dropping down to the 2nd energy state. Okay. So going from energy level 6 to number 2, and then 5th to 2, 4th to 2, and then 3rd to 2. Okay. There are other ways it can drop, right, as you can see here. So some of them are going from 6 to 3, 5 to 3, and 4 to 3, as well as the higher energy states going back down to the ground state. But they're all invisible wavelengths that we aren't able to see. So, and the same kind of dynamic will appear in all of the other elements that we're going to be showcasing here. But the hydrogen one is the most easily demonstratable mathematically. Let's let's see here. So this, let's see, how should I put this? Alright, so I think the best way to just, I think it's right about time we actually just go ahead and showcase this stuff. So, here, this is the emission spectrum of hydrogen, the one that I showed earlier, okay? So this, again, this is easily calculable. And the other ones that are at the far left part, right, that starts to extend towards the ultraviolet. They're very barely visible to the naked eye, okay? You will, if you were to view this through a diffraction grating, you would definitely see the red, the cyan, the blue, and then maybe, if your eyes are still keen enough, you can see this one here. Probably not these three here, okay? Our eyes are not that sensitive enough. Even my Android eyes aren't that sensitive, okay? So, by the way, epilepsy warning, this might involve some flashes that might upset people, but I will definitely be playing this, replaying the videos at a slower rate such that it won't, so that it shouldn't trigger an epilepsy reaction, but, so, just be advised, alright? So you can see that this was initially with the with it anchored on top of the, what was it? The sticky tack on the mason jar. There, you can see, like, one pancake has appeared here. And because I wanted to see more of them, I recorded another video, this time with just using my fingertips at the very end. Okay. So there you can see it even before it gets struck by the bolt. That's a good one. Well, that's a nice one. Blam! Look at that. Alright, so remember what I said about the specific energy levels of hydrogen, okay? So when the electrons are traveling through here, alright, they'll excite the atoms that are initially here, okay? And the colliding electrons will lose energy, right? They're transferring their energy to the electron clouds that will eventually emit light, okay? But since they've lost energy, they no longer have any remaining energy to excite other electrons within the gas chamber, okay? But remember that there's an electric potential active, and so they'll eventually accelerate along the gas tube until they'll gain enough energy to reignite and excite other atoms in the gas chamber again, and then they'll drop in energy, and then they'll excite again. And the process repeats until at the very end they'll accelerate towards the ground right at the very end here, okay? And then this flow of electrons will travel down into the Earth, okay? See if I can't find another good frame. Oh, that's a nice one. But even before, you can definitely see, like, especially in this frame, you can see 1, 2, 3, 4, 5 pancakes. There's a nice one. 1, 2, 3, and then a faint fourth one here. And then maybe a fifth here? But either way, yeah. Alright. So, next up, helium. Now, the spectrum of helium is a little bit harder to calculate. So, if you have a copy of Griffiths, right, he has a good example and demonstration on how it could be achieved by first doing a culmination of, since there's 2 electrons in the bunch, your electric potential is now doubled because there's 2 protons in the center. Excuse me. But you would do a combination of a ground state, of an electron in ground state, and then a hydrogen-like wave function that corresponds to another electron going around a screened charge. I believe that is generally the case. So, but what complicates things is that there's an interplay between the 2 electrons as well. So, because they're both occupying around the same space, and they also exert their own electric charge. So, so as you add more and more and more electrons to the mix, the spectrums become largely more and more complicated. These spectrums here have been computer calculated. These are not ones that are directly viewed from a spectrometer, but these are the notable frequencies that are possible. Okay, you would not necessarily see all of them when you submit these things to electrical discharge. So, all right. The helium emits this nice, brilliant, peachy white flash. Look at that. Look at that, it's like a Christmas tree. Wow, look at that. Isn't that amazing? I absolutely love this. This is just so good. Like, when I first did this, I was so excited to, like, it was like I was doing something like the slow-mo guys were doing. So, to seek out these specific frames, but yeah, just so wonderful. I think, like, it would be such a great pleasure to see if they actually did this. But one thing I would love to do sometime in the future is to actually get a diffraction grating and image these things through my phone's camera once again, by fixing the diffraction grating to the lens. So they're nice, cheap materials. I just don't have them on me right now, which is ironic considering that I have a Geiger counter, but just can't have everything all at once. Anyway, so up next, the next gas, okay, is nitrogen. Now, our atmosphere on Earth, as well as the space station, is 70% nitrogen, okay? Now, you'll see some frequencies here, most notably in the red and some in the blue here, and then you'll also see these mid-range or frequencies that are green, yellow, and teal, okay? But those aren't necessarily visible. Remember, it all depends on the available energy of the electrons, okay? But it emits this vibrant purple color. Look at that! And you'll notice that it's almost the same color as the actual electric discharge that you'll see that's emitting from the spark, okay? And that's not a coincidence. Remember that our air is 70% nitrogen, so it makes sense that part of the purple glow of the spark generator is purple, okay? And here you see the pure hydrogen within the chamber giving off the actual glow by comparison. You also notice that in some of them will not actually form streaks, or they'll not form pancakes. That's because the current or the electric flow just goes immediately to the ground, okay? Meaning that the electrons have enough energy in them to excite and discharge all of these frequencies here, okay? Such wild stuff. Alright. So up next is oxygen, and this one is one that I've been wanting to do for quite a while to get it actually demonstratable. The original setup involved when I first got these gas ampules. I also bought a plasma globe, very cheap novelty toy, and those are much more easy to handle. They have the glass dome about them, and it too exerts an electric field outside, and that would also excite the gas bulbs. But it was not enough energy to really excite oxygen enough, such that you could actually see anything flashing from the oxygen bulb. There was a faint signature, but not quite there. Now, one thing to note is that the spectrum that you see from oxygen is also what you primarily see when you're viewing Aurora Borealis. Okay. So the red frequencies, as well as the green that you see from Aurora Borealis, that's what it corresponds to, these frequencies here. Okay? So yeah. And the combination of the two, remember that it's a combination of frequencies that are being emitted all at once whenever you're looking at these bulbs. So it's seeing a combination of both red and green being emitted. And a little bit of blue there at the very end, probably. So yeah, if you were to analyze the spectrum of the lightning, you would definitely see a combination of all of the wavelengths between both nitrogen and oxygen. So you would see a combination of this emission spectra and the nitrogen emission spectra. And it would make sense, right? You know, because both those two molecules comprise about 90% of the atmosphere, about 95% of the atmosphere, I think. With I think about 2-ish% being argon, and then a remaining fraction being water vapor, and then an even tinier percentage was carbon dioxide. So up next is neon. And like I said before, again, this is the computer-generated possibilities of its spectrum, but you all know that neon is viewed red. You know, you mostly see the red. And if you view it even through a diffraction grating, you'll definitely see that it's mostly towards the red and a little bit of the green. Not necessarily much of the blue, because it requires a much higher energy for that to get excited to that state. Okay? Alright, this is also a good one. Look at that. Yeah, isn't that nice? Nice, big, orange flash. It's a distinctive, red color to it. And you also notice that that the red part, when it's outside, when there's yet to be a spark connection, right? The red parts are towards the ground, and the higher energy portion of the electric potential. So one can assume that what's happening is that it's striking here, losing energy, the electric current, and then it's accelerated steadily throughout this, emitting a nice stream of light here from other frequencies, and then it's accelerating again towards the ground. Alright, so chlorine gas. Alright. Now, historically, chlorine, bromine, and iodine have been used as the gas in halogen lamps. Okay, so halogen, the chemistry word meaning salt maker. Okay, so chlorine, bromine, and iodine have been common elements used in gaseous forms in bulbs because they produce a very good flash. They produce a very good light. So you can even see some more interesting colors. You can kind of see a little bit of yellow before the chlorine gets sparked here. So a nice demonstration of what it looks like fully lit up. Again, yeah, they're very bright. The halogen bulbs are very bright. Very nice. You'll also notice, yeah, you've obviously noticed at this point that there's a black vertical bar that's going between. That's just because the camera of the phone is trying to keep up with its frame rate is not quite in sync with the frequency of the Tesla coil. So that's what's, and since the Tesla coil is the primary source of light, it's just gonna be that way. And so anyway, right, the argon, probably one of my favorites, just because of its distinctive blue glow. Yeah. So this is the second noble gas, right? We saw the first one was helium. Okay. And you'll notice here, of course, it starts to light up before it reaches a spark. Nice white glow, and then a wonderful, like, soft lavender glow to it. Punctuated by this wonderful light, like silvery blue glow. You can see that where the large blue flash is occurring, it's going directly from the spark to the ground. Okay, the electricity is trying to follow the lowest point of energy, so. Alright, bromine. Okay. So, bromine, so in this particular case, so you chemistry majors will know that pure bromine, like very, the brown-orange liquid, is actually very caustic. I don't own that, by the way. Remember, these are all low-pressure samples, and they're so low pressure you can't even see their color when you look at them. So, do not be worried about any kind of toxicity from these elements. So, all of these are perfectly safe, even if they were to break. So, also a nice green here at these two ends. Wonderful, yeah, bromine is, I think, still used today, but I think the more prominent one is iodine. That's used for it, for halogen lamps. Okay, so this is krypton, the third noble gas. Okay. A lot of the noble gases are very good for lamps. The ones that you see around town are more or less emitting a whitish color, but then have a gel plastered over it to filter out the light. So to give that green look, because none of the elements here emit like a pure green glow just for example, or, you know, it's only in the case of neon that you get like a nice red color from it, or a nice distinct color. Or argon that gives a nice, bluish glow. But in the case if you wanted like a yellow lamp or a green neon lamp, so to speak, you would take your gas filament and then coat it with a gel or, something transparent that helps filter out the other wavelengths so you get that color. So, look at that. Nice. Since Krypton has a spectrum that goes across all the ranges, you get a nice, these nice solid streaks that represent the flash of the... Oh, shoot. Oh, shoot. Did I not... Oh, no. Hold on. I'll show Brahmin. Did it? Let me see here. I'm just hoping that... Okay. I'll scan back anyway to make sure that you all can see it. There we go. So you see these brilliant streaks as the current is passing through the gas, showing off probably nearly the full spectrum of Krypton. A testament to, its capacity for all the different colors you can filter out of it. So, iodine, okay. The one that is more than likely used for a halogen lamp. Iodine you're probably familiar with being in solid form at room temperature. It can be vaporized quite easily. It can sublimate if you expose it to a small amount of heat into this purple vapor. But again, you don't really see the color through the bulb. But anyway. There's that. Now also you might notice that, like, over here, right, at this end, there's a small speck, and that's actually a bit of iodine that has been left over from the process of making the ampule. Yeah. Nice soft white light. Kind of bluish in tint. The colors may be slightly altered due to the camera's sensitivity, so keep that in mind. But otherwise, it's pretty dang close to what you would see. Alright, and then I think this is the last one that I have here. Xenon. Okay. So Xenon is notable in the sense that it does give off a very bright flash. It's used in arc lamps especially, and it consists of taking, an anode and a cathode at very close range, enclosed in a glass bulb, subjected to high voltage, and inside is xenon under high pressure. And this emits an extremely bright flash. And there's its color. Yeah. Its spectrum emitted through across, its full spectrum being shown. Yeah, isn't that great? The flash is most visible towards where the spark hits in the ground. And then, like, one last one. It just arcs just as I'm about to set it down on the countertop. Bang. Yeah. Now these are all the gaseous elements. There aren't many. You might be, wondering, like, if there are potentially any more gases, but if you remember your chemistry, the only other gas that you can probably get is that is on the periodic table at room temperature is radon. But radon is unstable. It's an unstable isotope and doesn't last for very long. So to get it in a quantity like here in the videos here, it's just impossible. So um, it is emitted by uranium decay, but it's not in significant quantities from radon filtration that you would actually be able to make a sample out of it. And here's all of them together. We're gonna move. Wonderful. Gosh, it is like, I think it's, without the tools of quantum mechanics, the machinery behind all of this would be invisible. Like, it's just, I love having to know enough physics that I'm able to explain this to you guys and to showcase this. I hope in the future that I get to show off more of the elements and what they do, as well as many of their properties. The gases are such a great choice to look at, I think. They're all kind of distinct one way or the other. The chlorine and bromine are kind of similar, but, for the most part, all of them have their own unique, show. And I hope in the future that I'm able to, get a diffraction grating and, take some pictures of their spectra. So, yeah. Thank you so much for joining me on this short special. And, yeah, I'll see y'all next time.